Okay, so first of all, I would like to thank all of you for submitting your task one for your assignment. I have received all your submission. So please proceed to do the next part of your assignment. The due date is next week for task two and task three. So please take note on what you need to do for your assignment. Yeah. Okay, so we will continue on discussion for this course for chapter 4, the second part of chapter 4. We are still at our relational model. We will be discussing on more on relational algebra. Okay, so we'll discuss more on relational algebra. We will continue from last week. Last week we have looked at various relational algebra like union, intersection, projection. Uh, so for this week we continue on some other type of relational algebra, and today we will also look at the basic concept of query processing and also query optimization. Yeah, so we continue to the next example of relational algebra. So we have this outer join. So this outer join, it's a type of join. Okay, it's another type of join. So if the join operation that we have, it combines data from two tables by forming a pairs of related rows where the matching columns in each table have the same value. That's for join. Okay, so for so if one row of a table is unmatched, okay, so in join, if one row or one tuple of a table is unmatched, the tuple or the row is omitted from the result table. So this has been the case for the joins that we examined earlier last week. So to overcome this case, like because if in the traditional join, if the row is unmatched with the other table, will be omitted. So the ISO standard, they provided another set of join operators which called this outer join. Okay, so this outer join, what it does is that it retains the row or the tuple that do not satisfy the join condition. So this outer join, it will display rows in the result that do not have matching values in the join column. Okay, so those rows that is omitted with join operation. So this outer join will be used to still include the omitted result in the result table. Okay, so the outer join, it's becoming more widely available in relational system and is a specified operator in the SQL standard. So we have the advantage of this outer join is that information is preserved, means there's no result or there's no rows is being eliminated from the result of any operation. Okay, so outer join, it preserves row that would have been lost by other types of join. Okay, like example, the previous week we have discussed about join. Um, it will actually like omit or discard the rows that do not satisfy the condition of the join. So this outer join will actually preserve the data that was omitted for the join operation. Okay, so this outer join, we have two types. Okay, we have two types. We have the left outer join. Okay, left outer join. So this left outer join, it refers to the left table. We look at the example of this, and then we have the right outer join, with the which will refers to the S table. Okay, the right table. So this left or also known as natural auto join. It keeps every rows in the left hand relation in the result. Okay, so it refers to the left hand relation. Left hand should be R. Okay, we look at example after this. So similarly, for right outer join, it will keep every rows in the right hand relation of the operation in the result. Yeah. So we look at left outer join. So first, left outer join. This left outer join is a join in which tuples or row from R, yeah, the left table do not that do not have matching values in the common attribute of S. So it will also be included in the result. Okay, so those row that do not have any relation with the attribute that we have in S will still be included in the result. Okay, if you notice here we have A1. So A1, we have B here, the column B. It it matches with B under S, and then C is X, so we get A1X, right? And then we have the second one, A1 matches with this, and then we get this result. And then we have B2, okay? So B2, here B and 2, these two does not match with any attributes under this table S. So, but in normal join that we have discussed previously, it will omit this row, right? But for outer join, it will still be included in the result, okay, which will be shown like this, and C will be represented as null. Okay, so for this outer join, we will have in our result there will be some tuples or some row or some column that do not have any value, which we will label it as null. Okay, so missing values in the second relation are set to null. Okay, so null. There's nothing because there's no match between this table and this table for this row, the second row for the second tuple. Okay, so left outer join is join which rows from R that do not have matching values, do not have any matching values from here, no matching value here. Okay, of S that are also included in the result relation. Okay, so we still include this in the relation. So that's the basic concept of left outer join. Okay, so let's now look at example of left outer join. Okay, so we have this employee and department. So this is R, this is S. Okay, so we will be looking at this attribute department name. Okay, so you see we have the second row here, cells. So cells we have area, right? So it is listed here. Okay, so we go from the top one. Okay, so we have Harry, and then the department name is finance. So here we don't have any finance, but we still send this row to the result table. Okay, so we put the information or the data from employee, we send to the result table, but the manager will be null. Okay, this is the omega symbol or also represent the value null. Okay, and then we have Sally cells. Okay, so we have cells here, so we can just put it in the result table, the manager Harriet, and then the next table or the next row is finance. So we don't have finance here. Okay, but we still put it in the result with null value for manager. Okay, and then another cells. Okay, cells. So we have cells. We will have value for manager because it's here, and then executive. Okay, executive. So we have executive and null. Okay. So because this is left auto join, we will not look at the row that is listed at the right side table. We will not take this production charts. We will not put it in the result. Why? Because this is left auto join. We will only include those row or tuples that in the left side table in the result. Okay, we look at example for right auto join later on. Okay, so let's look at example of this is a relational algebra operation. So we use this left auto join to produce a status report on property viewings. Okay, so in this example, we want to produce a relation consisting of the properties, okay, the properties that have been viewed with comments, okay, that have been viewed with comments, and those that have not been viewed. Okay, so this can be achieved using this auto join in relational algebra statement. So we have projection. We use projection. We will look at the property number, the street, and also the city for and the property for rent table. Okay, so we project the attributes of property number, the street, the city from this table, and then we do the left auto join for with viewing. Okay, with viewing. So we refer to these three columns or three attributes here, and then we auto join it or we left auto join it with property number. Okay, so we look at the property number. Okay, so the result is this. So we have the all the property number is listed. Okay, together with the um, together with those that have no comments. Okay, so all here, the one that has no comments from here will still be included in the result. Okay, so we have PA14. Okay, we have it too small, and then another BP for PA14. We have no dining room, and then the next one is PL94. Okay, so PL94, and then also PG21 and PG16. It's not listed here. Okay, so we still include them at this result table. So this is what we call left outer join. We refer to the tuples or the rows that we have here at the left side, those that have no matching value with the other table for the joining operation will still be included in the result. Okay, so let's now look at how we can use SQL to list branches and properties that are in the same city along with any unmatched branches. Okay, so in SQL we use this left join operation to 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 get this desired result. Okay, so in this example, the left join here includes not only those rows that have the same city, but also those rows of the first, okay, of the first or the left table that are unmatched with rows from the second table. Okay, so this left join will refer to the first table. It will still include the result that is unmatched with the rows of the second table in the result. Okay, So this is how we write a left outer join in SQL. Okay, so that's for left outer join. So we always look at the left table. Okay, the left table here. Okay, so how about right outer join? Okay, so right outer join, it's the relation of R and S that's written as this. Basically, it's the other way around for this. Um, like the middle of this. Okay, so it's shown like this. The symbol is this. So the result of the right outer join is the set of all combinations of tuples or row in R and S that are equal. Okay, so this is um, the rules for a normal join. We look at the combination of rows that are equal in the common attributes names, which the attribute from R and S refers to the same attribute name, and the row it matches. Okay, but in addition to that, it will also get or take the tuples or the row in S. Now we look at S. Okay, so it will for right outer join, it will refer to the table S or at the right side table that have no matching tuples in R. Okay, so this refers to S refers to the right side table and R refers to the left side table because this is right outer join. It will take all the result from it will take all the row from S that has no match with R and put it in the result. Okay, so let's now look at the same example just now. We see for the left outer join. Okay, so I just go back and show you. So previously, we referred to this table, right? So now we will be referring like this one for right outer join. We will refer to the right table. Okay, so we'll always look at this and refer to here. Okay, so we have cells, and then we will look at cells here. So we have the second row here. So we put this to the result table. Okay, so because we are looking at this S table now, the right side table, so we will not look at this at all. Okay, because we don't have finance here. And then we have a set. We still have cells here, so we take this and we put it in the result table. And then there's no more cells, so we look at production. Okay, so production join with employee table, the hour table. There's no production here, right? So for outer join, we will also include this tuple into the result. Okay, with the attribute, some attribute from with the attribute from R assigned with null value. Okay, so the result of the outer join, it is the set of all combination of row R and S that are equal to common attributes, and also in addition to the row of S that have no matching tuples in R. Okay, so this is R, this is S. So we always refer, if it's right, we'll always refer to the right side. Okay, got it?
Right.
Okay. So let's look at how we can write this in SQL. So the operation will be right join. Okay, so we want to list branches and properties in some city and any unmatched properties. Okay, so in this example, the right outer join will include not only those rows that have the same city, but it will also include uh, all the rows from the second table or the right table that are unmatched with the rows from the first table. Okay, so it's the other way around with left join. Okay, so the columns from the first table will be filled with nulls value. Okay, so that's this is how we write it in SQL. Okay, so that's for outer join. So next we have this semi join. Okay, another type of join. So this semi join it defines a relation that contains the row of R that participate in the join of with S, which satisfy the predicate of F. Okay, here here is listed B. Okay, but usually we look at basically it refers to a predicate. Okay, so the semi-join operation it performs a join of two relation and then projects over the attributes of the first operand. Okay, so one advantage of this semi-join that it decreases the number of row that need to be handled to form the join. We look at example after this. So it is for this semi-join, it is particularly useful for computing joins in distributed systems. So basically you have this example here. So you semi-join which you have a predicate here. We are only interested in seeing only the attributes of the staff relation. Okay, so we only want to see the staff relation. We use this semi-join operation. Okay, so this one is selection. So we will select uh, the city Glasgow because we want to list complete details of all staff who work at the branch in Glasgow. Okay, so it's specific. It's specific that it want to check all the staff from staff table, and then we will be referring to the staff branch number and also the branch number at branch table. So we have two here. Staff table, we look at the branch number, and also at branch table, we look at the branch number. Okay, and then we want to select city of Glasgow in the branch table. Okay, so we select Glasgow city, look at Glasgow in the branch table. Okay, so this is how we express semi-join operation in relational algebra. Okay, so the resulting will be the result is this. So we have this Glasgow with branch number B003. So from the start, the query, the relational algebra will look at branch number and look at the value B003. Okay, so we have three here, B003, and this, so it will be included in the result. Okay, so we have this, all this referring to the branch number of Glasgow. Okay, B003 is for Glasgow. So this is the result of this relational algebra. So how do we express this in SQL statement? Okay, so the query for this semi-join, we will be using exist. Okay, exist. So this query, it could be refresh this one. It can be rephrased as find all stuff such that there exists a branch row containing his or her branch number, which is the branch number here, and the branch city equals to Glasgow. Okay, you select all information from staff, okay, which we assign it to this attribute as where we use the exist query for semi-join. We give the predicate here. So we select all from branch, which we declared as B, where S, okay, S refers to staff table, refers to the branch number in staff table, equals to B, okay, B from branch table, B the branch table refers to the branch number, and then we use another operation here, the logical operation. We have and, okay, and must satisfies this, which will refer to the city as Glasgow. Okay, so city as Glasgow. So this one will be referred from branch table. Okay, so this is how this is for semi join. Yes, this is for semi join on how we can write it in a SQL statement. Okay, so semi join uses exist operation. Okay, so far okay.
Okay.
All right. So next, another relational algebra we have here is division. Okay, so division we have this. This is how we represent it. So the division operation, it defines a relation over the attributes B that consists of the set of tuples from R that match the combination of every tuple in S. Okay, so it defines a relationship over the attributes B that consists of the set of tuples that we have in R, all that we have in R, and that match the combination of every tuple in S. Okay, so if we look here, we have one, this one matches. So we'll take the, when we use this division, it will take the result of A attributes. And so if this one, this matches right, so it will give the result with the value at the attribute A, double A. Okay, so we have A, and then we have another one, B, and for this one, B2. So you get B, this one. Okay, so we'll get this result, A, B. So it refers to this one. Okay, so let's look at the example here. The real situation example. So let's look at how this division is used for this for this table. So we want to identify students who has completed database 1 and database 2. Okay, so we refers to the common attribute of B. Okay, this is attribute B. So we refers to database 1. Okay, so it must fulfill for both. Must fulfill for both means the student must complete both database 1 and database 2. Then it can be included in the result. Okay, so we have this database 1 and 2. So we have Fred uh, finishes the task database 1 and database 2. So it goes to the result. And then we have Eugene, because Eugene did not complete there's no row that stating that Eugene have completed database 2, so it will not be included in the result. And then we'll have Sarah, who have completed database 1 and database 2. Okay, so it will be included in the result. Okay, so this is R. This is sorry. This is R. Completed table is R. So we have A attribute, B attribute, and B attribute at S. Okay. So every time we use this division operation, we'll always look at B the B tuples. Okay, which satisfy uh, which matches with the B B attribute in R. So we will get the result. Okay. So let's look at another example of this division. So we want to identify all clients who have viewed all properties with three rooms. Okay. We want to identify all clients who have viewed all properties with three three rooms. Okay, so for this for this situation, we can use the selection operation. Okay, the selection operation to find all properties with three rooms equal to three in the property foreign table, and followed by the projection of a projection operation. We have projection operation here to produce a relation that contain only these property numbers. Okay, so we have this projection. So we have this projection from viewing, and this projection for looking at the property, this property number, and also we select the rooms from the property for rent table with three rooms. Okay, so let's look at the result. We get CR uh, 56. Okay, so we look at the property number. Okay, all properties with three rooms. So you select, you include the property number in this attribute with rooms that has three rooms. Okay, so meaning to say these two property has three rooms. Okay, and then you do the division with this viewing table. We will look at the property number, and we see which row satisfy these two. Okay, so we have PG4 and PG36 here with the same client number. So that's why we get this result. Okay, so the division, it refers to the uh, the B row or B attributes in S. Okay, so it always, it must fulfill everything under this attribute and find a match from the other the other table according to the to be attributes, and then you will get the result from the A attribute. Okay, so this is the result. Okay, got it.
Right.
Okay, so we take 5 before we continue to this next part. Okay, let me take 5 here. Okay, can we continue?
Okay.
Benar. Okay, so for before we go to this, we in database we often want to perform some form of summation. Okay, we want to do summation of data, also known as aggregation of data, which we want to produce a total at the bottom of a report, right? So in other situation, we also want to do some form of grouping of data, which similar to us wanted to provide subtotals in a report. Okay, so we have this aggregation of data and also grouping of data. So aggregation is where we want to get totals for the report, and grouping is when we want to have a subtotal in a report, right? So this operation of aggregation and grouping, it cannot be performed using the basic relational algebra operations that we have discussed earlier. Okay, so the previous basic relational algebra operations, it is not it is not able they are not able to perform this aggregation of data and grouping of data, right? But there is an additional operation that has been proposed, which is this aggregate operations. And also we also have another one after this, grouping operations. So we have let's now just we discuss on these two operations. So first we look at aggregate operation. So it's represented as this symbol, okay? And this aggregate operation, it applies aggregate function list, okay? The AL, aggregate function list is AL, to R, okay? To R, to the table to define a relation over the aggregate list, okay? Over the aggregate list. Okay, so this AL aggregate list, the aggregate function list, it contains one or more. You can have our aggregate function and also an attribute pairs. Okay, it can have one or more. Okay, so here if you see an example here, so this is the AL for this situation. We have it's using the aggregate function of count, and you have the attribute, okay, and another aggregate function refers to salary from the table stuff. Okay, so we have these main aggregate functions. We have count, sum, average, mean, and max. Okay, so you can apply this to your assignment as well when you do the queries later on. Okay, so count, what's the purpose of count? It returns the number of values in the associated attribute. Okay, so when you use count, it will it will return you a number of values that's associated with this attribute. Okay, so how many stuff number? And then the sum, okay, sum, it returns the sum of the values in the associated attribute. Okay, so sum will give you the sum of the values in the associated attributes. Okay, so for count, it gives you the number of value, how many stuff number. And then sum will give you the the summation of the values that you have in salary. Okay, so for average AVG, it returns the average of the values in associated attribute. For mean, so this one a minimum, it returns the smallest value in the associated attribute. And then we have max. So this one will return the result of the largest value in the attribute. Okay, so count gives you the number of the attribute. Sum give you the summation of the value in the attributes. Average the average values of the attributes. Mean the minimum value, and max the maximum value. Okay, so we go back to this example. We have a count aggregate function. Mm, you want to count how many staff number, and you want to sum up, you want to have the summation of salary according to the from the table stuff, from table stuff. Okay, so here this is how we represent the aggregate function in SQL query. So now we want to find a number of managers and sum of their salary. Okay, so we want to find managers and sum of their salary. Okay, so you select count aggregate function. Okay, you want to count the staff number, and then you define or you declare it as my count in the result, and then you will sum the salary and you declare it as my sum in the table in the result. So this one you get from the table stuff, and there is a condition here where the position of this is equal to manager. Okay, equal to manager. So here the result shows you the there are two managers. Okay, two managers, and the sum of the the summation of their salary is 54,000. Okay, so restricting the query to manager is achieved using this where clause. Okay, so we use this restriction, which it will only find the number of managers in this staff table. Okay, under the staff number, and then the number of manager and the sum of the salary can be found by applying the count and the sum function respectively to this restricted set. Okay, so it will only count and sum up, you only count the staff number and the sum of salary, which the position is manager. Okay, so this is a restriction for the SQL statement. So let's look at another example here for this aggregate operations. So how many properties cost more than 350 per month to rent? Okay, so we use this operation. This is the representation of a relational algebra for these aggregate operations. So we refers to the we will we rename this one rename to my count for the result, and then you do the aggregate operation. You count the property number. Okay, you count the property number which satisfy this the selection where you only take the result of rent that is more than 350 from the table property for rent. Okay, so I repeat. So this one, this symbol here is rename. Okay, so you rename in the result. Okay, you rename the attribute as my count, right? And then we use aggregate function, aggregate operation. We use the function count, the property number. We count the property number, and then we have this selection of this restriction more than 350 from the table property of for property for rent. Okay, so you will refer to the rent attribute and see, and it will check, the query will check how many property number that has more, that the rent is more than 350. Okay, so this is the result. So you have my count, which you already declare here. You rename the r table as my count. Okay, and then you get the result of 5. So this result of 5 is the count of property number. Okay, so we have here we have 650 more than 350. 1, 2, 3, 4, 5. Okay, so we have one equal to 350, but this the restriction is that it must be more than 350. Okay, so if you refer to the property number, you have 1, 2, 3, 4, 5 property that has rent more than 350. Okay, so that's why you get 5. Okay, so that's for aggregate operations. So next we look at the grouping operation. Okay, so we have aggregate operation, and then we have this grouping operation. So this grouping operation, it groups the tuples or the row of R by grouping attributes, which refers to GA in this grouping operation, and then applies the uh, aggregate function list DAL to define a new relation. So here DAL, similar to aggregate operation, DAL can contain one or more aggregate function and attribute pairs. So the resulting relation that contains the grouping attributes, the GA, along with result of each of the aggregate function. Okay, so this one we add up. This one is from the aggregate operation, right? So for grouping operation, we apply the GA as well, which it groups row of R, and then apply the aggregate function list of AL of this one for referring to table R. Okay, so let's look at the example for this grouping operation. So we want to find the number of staff working in each branch and the sum of their salaries. Okay, so we want to find the number of staff, find number of staff working. So here you already know we will be counting, right? You count and the sum of their salary. So we already know we will use the aggregate function of sum. Okay, so here you do the rename for the result. You will look at the branch number, okay, branch number, and then you will count this number of staff working, and you will also want to view the sum of the salary. Okay, so here the GA, the the grouping attributes is according to branch number. Okay, so you want to group by branch number. So this is the grouping operation. You want to get the result of referring to branch number, and then you satisfy the the aggregate operation, which you count the staff number, and then you sum up their salary referring to the table staff. Okay, so I repeat you for this grouping operation. you want to refer to an attribute, you group into attribute. So you will be referring to the branch number, where you will include in your result the branch number, the number of staff working in each branch number, and the sum of salary of those staff working at the branch. Okay, so here from the staff table, we will be referring to the branch number attribute. If you refer to this, and then you will count you will count how many the branch number how many. So we have here, usually the result will give you the the most the most higher count. Okay, so you have B003 here with 3, 1, 2, 3. Okay, so you have 3, and then you sum up their salaries. Okay, so it means you sum up 12,000, sum with 18,000, and plus 24,000. Okay, so you will get this 54,000. And then we have the second branch number, B005. So you have two here and at the bottom, at the top and the bottom. And then there are two. Okay, you count the branch number two. And then you sum up their salary, 30,000 plus 9,000. Okay, so you get 39,000. And then the the lowest count is B007. B007. So you sum up, because it's only one, so you get the value of 9,000. Okay. So in this case, in this scenario, we first need to group the tuples. We need to group the row according to the branch number. Okay. And then we use the aggregate function of count and sum to produce the required relation. Okay, so we have this branch number. You want to know the branch number, and then the count of the branch number, and the sum of salaries of the staff working at the branch number. Okay, got it?
Okay.
Okay, so let's look at now. Let's look at how this is represented in SQL query. Okay, so we want to find number of staff in each branch and their total summary is total salaries. So we find number of staff working in each branch and their total salaries. Okay, so the same scenario just now. So we select branch number, and then we want to count the staff number, and you declare it as my count, and then you sum this their salary as, and then you declare the summation as my sum from the table staff, and then you do the grouping. Okay, so for grouping operation, you use group by. Okay, group by branch number, and you order by branch number. Okay, so here is the view of how this query is being done. So first, the SQL will divide the staff into groups according to their respective branch number. Okay, so it will be grouped by branch number. Okay, so this one group by branch number. So within each group, all staff have the same branch number. Okay, so here the staff here, the list will have a same branch number. Okay, branch number is B003. So for each group, the SQL will compute the number of staff members. Okay, compute the count, the sum, sorry, the number of staff member, and it will also calculate the sum, the salary in the salary column to get the total of the salary. Okay, so here SQL will generate a single summary row in the query result for each group. Okay, so group it will be grouped by branch number here. Okay, so finally we will get the result. The SQL will provide you with a result of which is sorted in ascending order of branch number, branch number, this one. So it will be ascending order, okay, from the small number of branch number to the biggest number, ascending. Okay, so that's how conceptually how this SQL query is being performed. Yes, select branch number, count the staff number, and declare as my count. And then you sum the salary, and then you sum the salary, and then and it declared it under my sum from the table staff, group by branch number, and it order by branch number. Okay, so far okay.
Okay.
Okay. All right. So, so we have finished looking at the relational algebra in this lecture for from last week and this week. So now we will look at the second objective of this lecture. We will be looking at query optimization. Okay, we have this query optimization. So the aims of query processing are to transform a query that is written in a high level language. So high level language here we refers to SQL query into a correct, we want to this the query processing, we want it to be correct and efficient. uh, we want to use an efficient execution strategy, and we want to express it in a low level language. Okay, so the high level language is referring to the SQL query, and the low level of relational algebra expression is referring to the this one is grouped as the low level language. Okay, so we have the high level language and low level language. Adana, give me a sec. Okay, so um, so we for query optimization, we want to run the query processing in efficient way and in a correct way. Okay, so this figure here shows us how we can achieve that. So we have these basic steps in query processing. We have parsing and translation, and then we have the optimization and also evaluation. Okay, so we have parsing and translation, and then we do the optimization, and then we do the evaluation to get the query result. Okay, so we look at this one by one. So for parsing and translating, so what happened in this stage is that it will translate the query into its internal form. Okay, basically it is translated into an expression of relational algebra. Okay, so the parser will check syntax, it will validate the relations, the attributes, and also access operation, access permission. Okay, so every time we run a SQL query, there will be a parsing and translating process, which the translating will happen when the query is translated into its internal form, basically to translate the SQL query to relational algebra expression. Okay, the expression or the operation that we have discussed from previous week and this week. And then the parser here will check syntax from the query to validate relations, checking the attributes and also checking the access permission. And then we have the optimization. So from here, it will be optimized. The expression will be optimized by finding the best execution plan for the query. Okay, so here it can refers to statistics in the DBMS. And then it will go to the execution plan. Here is where it will goes to the evaluation engine, where the query execution engine takes a physical query plan. Also, this one it takes the execution plan, which is the physical query plan, execute the plan, and return the result. And you'll get the result. So these are the basic steps in query processing. So every time we query, uh, we query, we do a query processing from high level language. There will be parsing and translation to a relational algebra expression, and then the optimizer will check the best execution plan for the query, and the evaluation engine will take the execution plan and provide us with the result. Okay, so this is the basic steps in query processing. So query optimization, it's the activity of choosing an efficient execution strategy when you want to process a query. Okay, so generally what we want to do with this, why we want to do this query optimization, we want to try to reduce the total execution time. Okay, um, we want to reduce the total of execution time of the query, because this one is something to do with the resource usage. Okay, usage. So this the time of execution time of the query, it's the sum of the execution times of all individual operations that make up the query. Okay, so there are many equivalent transformation as of same high level query. So the aim of this query optimization, we want to minimize resource usage. Okay, so this refers to the total execution time of the query, right? So this resource usage, it may be also viewed as the response time of the query, in which case we concentrate on maximizing the number of parallel operation. Means you can run more operation um, and give good response time. Okay, basically query optimization is for you to minimize resource usage. We will have an example. We have this example. So let's say we want to find all managers who work at a London branch. Okay, so we will select all from staff table and branch table, where the staff branch number equals to the branch number. And you also want the position from staff table to be manager. Position is must be manager, and from branch table you want the city to be London. Okay, so this is an example of a query, right? So if you notice, like this query, like you need to check from staff, and then you declare staff as S, branch as B, and then you have this restricted restricted condition where you want the branch number from staff must be equal to the branch number of B, branch number of branch table, and so this is another operation. You want the position in staff table to be manager, and the city from the branch table is London. Okay, so like by thinking of it logically, right? The query will need to do some the query will be like taking up you need to like when you run this query, right, you need to like follow from you will need to do few things for you to fulfill this query. Okay, so in this case we don't look at we will not be looking at the we will not be looking at um, the result. Yeah, now we are looking at the query optimization, which we will be looking at the the resource that are used for running this query. Okay, so here from this example here, okay, so we have this is the SQL statement, right? So after you have the SQL statement, the SQL query, you will have the relational algebra expression. Okay, so from the SQL query, it is translated to the relational algebra expression, which is the RA. So for this example here, there are three equivalent RA queries. So there are three relational um, relational algebra queries that you can translate from this high level language to the low level language of RA. Okay, so all this will give you the same result. So we have selection, and then we have another one join. Okay, so from here, the queries, we will look at which one uses more resources for this particular query. Okay, so we'll discuss the how do we find or how the queries is being selected for the execution plan. Okay, so for this example here, we assume that there are 1,000 tuples in staff and 50 tuples in branch. Okay, for the purpose of this as example, we want to assume that we have 1,000 rows in staff and 50 rows in branch. And then we also want to assume that there are 50 managers that are working uh, in five London branches. Okay, and then we further assume that the tuples are only accessed one at a time. Okay, so for the query to run, we assume that the tuples here is accessed one at a time, right? So the result of intermediate operations will be stored on disk. So this is where the resources will be used. Okay, so now we will not look at the result of the query, but we look at how this SQL query take up the resources in for running this query. Okay, so the three equivalent queries are these. So we want to compare these three queries based on the number of these accesses required. Okay, so now we want to compare these three. These three will give the same result. It's all usable, but we want to compare these three queries uh, based on number of these accesses that is required for each one of these. Okay, so now let's look at the first query. Okay, so the first query, this is not the result. Yeah, this is these accesses required. Okay, so let's look at this. So the first query, it calculates the Cartesian product. So this is Cartesian product. This is Cartesian symbol, and it calculates the Cartesian products of staff and branch. Okay, staff and branch. This one, staff and branch, which requires 1000 plus 50 these excesses. Okay, so it will this query itself, the Cartesian product, will use up these excesses with this 1000 plus 50 to read the relation and creates a relation with these tuples. Okay, so this query will access the Cartesian product will access this with this resources and to produce the relation with this calculation with this excess. And then we have to read each of these tuples against to test them against the selection predicate. Okay, so we have another selection predicate here at a cost of 1000 times 50 these excesses, giving a total cost of this excess, okay, 1000 100,000 101,050. Okay, so this is the total of this excess for this query. Okay, so we have Cartesian product and we have a selection operation. Okay, so that's for the first query. Now we want to go to the next second query. So we have this join operation. Okay, so join operation, we have join operation here. So we have the join operation of staff and branch, which again requires the query of the this access to read each of the relations. Okay, this one at 1000 plus 50, and then one for each member of staff. So, and a member of staff can only work at one branch. So consequently, there's a selection operation here which requires 1000 this access to read the result of the join and giving the total cost of 3050. Okay, so we have this second operation with these excesses of this. Okay, so this is based on this assumption. Yeah, so let's look at the last query, last relational algebra. So we have the final query that first reads each of staff tuple to determine the manager tuples, the manager rows, which requires 1000 these excesses and produces a relation with 50 tuples. Okay, so we have the staff tuples and the branch tuple. Sorry, this one. So this one is for the third one. This one for second one, right? So this one for the third one. So we have the it first read each staff tuple we have 1000, and then determine the manager tuples, which requires this excess of this. And the second selection, we have this second selection. It reads each branch tuples, the 50 tuples in branch, to determine the city, London. Okay, which will require 50 these excesses, which produces a relation with 5 tuples. Okay, so the final operation of join, right, of the reduced staff and branch relation, which requires only these excesses. Okay, so it will give a total cost of 1160. Okay, so first it read 1000 staff, 1000 staff, and then it writes 50 managers and read 50 branch, writes the 5 branch in London, and then it reads the managers, the 50 managers, and the five branch to create the final join. Okay, so the total this access for the third query is the lowest one. We have 1160. So clearly in this case, the third option is the best in this case. So this is what happened when we want there is a query optimization. So the query optimization will find out which execution plan is suitable for the query so that it will not take up the these accesses or the resources of the query process. Okay, so Cartesian product and join in the first query are much more expensive. Okay, we can declare this as expensive than the selection operation that we have here. Okay, in the second one. But the third option here, it significantly reduces the size of the relations that are being joined together. Okay, so this one we are studying the query optimization. We look at the equivalent relational algebra queries, and we look at this accesses number. So from there, the query optimization will pick which execution plan is the best, and then proceed to the next to give you the result. Okay, so this is the explanation of each one of these. So the first one will read 1000 stuff, and then it read 50 branch, and then it write 1000 times 50 records, and it will read 1000 times 50 records to search for the result. Okay, so this one is done 2 times. Okay, for the second query, it will read the 1000 staff, read the 50 branch, and then the join creates 1000 row of staff branch data, and then there will be write and read operation. Okay, so for the third operation, it read 1000 staff and then writes the 50 managers, and then it read 50 branch, write 5 branches in London, and then it reads the 50 managers and 5 branches to create the final join. Yeah, so this slide here shows you how you uh, define this access for the queries. Okay, so this is query optimization. You want to get the best query result that will not take up all of your resources. Okay, so far okay, can understand, yeah, this query optimization.
Yeah.
Okay, so this one, now we have this one. I think this is the last part of this lecture. So we will now discuss aspects that is sometimes used to improve the performance of queries. So we have this evaluation of expression. We have strategy one by using materialization, and the second strategy is pipelining. Okay, so the result of intermediate results in relational algebra operation are written temporarily to this. Okay, so it this materialization, it use intermediate result materialized in temporary relation to evaluate the next level operations. So the output of one operation for this what strategy one, it is stored in a temporary relations to process the next operation. Okay, so there's another alternative approach for this, which is the pipelining. So this pipelining is to pipeline the results of one operation to another operation without creating these temporary relations which will be holding the intermediate results. So clearly if we can use pipelining, we can save the cost on creating this temporary relation because there's no storing of this temporary relation, but it will read the results back again. So pipelining, also known as stream-based processing or on-the-fly processing. So it avoid constructing temporary result as much as possible. So this one obviously will save more cost. Okay, so let's look at the first one, materialization. So for this materialization example here, first it will compute and store the selection the selection operation with price more than 5,000 stored at the order details, and then it will compute and store join of customers and orders. Okay, join, and then it will join these two materialized relation and project onto CNAME. Okay, so it it will this materialization is store the query here, store here first, it do this first, and then it do this, then it join the two to and it project to this name, CNAME. Okay, as for pipelining wants a row from order details satisfying the selection condition. This one, after the selection condition has been found, pass it to the join, pass it onto the join, and then it does not store the final join but pass the tuples directly to the projection. Okay, so the previous one, the materialization, it does this and then does this first and then it goes up. Okay, so for pipelining, once this is satisfied, it will send the query or the result directly to the projection. Okay, so that's for materialization and pipelining. Do you have any question
No.
so far? Okay, ah? Okay, so that's all for today's lecture. So in this lecture notes, there is an exercise here. This one is actually taken from the ebook. You can try to do it if you want. This one is you can refer to page, if I'm not mistaken, page 190. The this one version from this ebook. Okay, you can refer to this ebook or this one. I think this one I already provide to you in the Google Drive. So you can refer to the Pearson book to look at this exercise. Okay, but I don't make this compulsory for you to do. Okay. So any question? No question, yeah. Okay. So I already announced in the group, but I announce again. So for your midterm test, it will be online test. Online test. Obviously, it will be open book. Okay, so it will be open book. Is there any news? Going back to campus. Do you all get any news? Did you all get news on going back to campus? Anyone? Teda. So far no news. Oh, March 1st. I see. Mm, so far it's been announced going back next Tuesday. Next Tuesday. But have to see this by then. Yeah. Yeah, still need to wait for. Yeah, I was also informed that we need to go back to the campus, but well, from what I know, it's compulsory for the staff, but the student, macam both not confirm yet lah for staff and student, not sure yet. You, the number of COVID cases is very worrying, right? Okay, so Kelvin asked at campus use our own laptop. If it's done during lecture time, if it's done during daytime, you can use your own laptop, or I will maybe if like I'm given a choice to run your midterm test, I will do it during practical session. Okay, because if it's a practical session, we will have apa itu we will have a lab assigned to us. Okay, so that you can like use the computer there to do your midterm test. Okay, but of course you can use your own laptop. Campus have labs, but they usually yeah. Uh, if you have your own laptop, you can bring your own. Yeah, because these calls require you to have a database, right? So maybe it will be good for you to use your own, because the database you created in your system, in your laptop, in your machine. Yeah, like what you mentioned. Okay, so our midterm test will be in week 8. It should be, it should be. I'm not sure how it will look like, but maybe you can get. I have not seen yet, but maybe you can look at the previous final final exam, to get some idea on how it will look like. Okay, but of course not as difficult as what final exam is lah. I don't know what I don't mean it's difficult. Not as much as what we have in final exam. It's half because it's 50 marks. Yeah, I have not seen the question yet. So, do you have any other question for the midterm test? So, if it's night time, I hope everyone okay if it's conducted night time. For that, of course, you will use your own machine lah at home. Okay, I will update you again if there's any update. So, any more question for midterm test, or maybe for for your assignment? So please start doing your assignment for this next submission, yeah? So you can already do the DDL and also uh, injecting your data records into your database. You can already create your tables according to your ERB. Okay? No more question. Okay, now. Mm, 4 groups. Okay, 5 groups coming assignment. Um, Solomon, can you submit in Google Docs format? You are doing this, you are doing your report in your own machine, is it? Not using Google Docs. Solomon, Solomon's group is who here? Ian and Russell, right? You submit your task one in Word format. It's okay for this, for the first task, it's okay. Maybe next task, you submit in Google Docs. Can you do that? Group, Solomon, Russell, and Ian, kan? Okay. The next task, submit in Google Docs. Okay, so you still have like 15 minutes. Do you have class after this? Not right after this lah. Not right after this. Okay. I might have some news for you next week. Some update for this course next week. I will let you know after I get a firm decision for this course. Okay. If you have no more question, I let you do your own stuff now, but you leave the session at 10:50. Can you do that? Maybe you can look at the task for uh, next submission. Yeah. Okay. So thank you so much, everyone. Leave the session at 10:50. Thank you.